Good morning, everybody. My name is IsaiahLerman, and I am presenting my project on wildfire mitigation in the Sulphur Springs Valley of Arizona, a case study of cost and risk for Sulphur Springs Valley Electric Cooperative, also known as SSVEC. So background of my project, SSVEC is a not-for-profit member-owned electric utility serving over 60,000 meters across 4,100 miles of line in southeastern Arizona. The purpose of my project was to identify SSVEC electrical infrastructure within wildfire zones and to help mitigate wildfire risk and costs for SSVEC. The wildfire zones, SSVEC conducted an internal study and identified 447 wildfire zones. And those wildfire zones were reduced to 30, which contained SSVEC infrastructure. The 2011 Monument wildfire burned over 30,000 acres, 84 structures, SSVEC infrastructure, and caused SSVEC to de-energize sections of its grid to protect its infrastructure and the public. The estimated cost of damage by the fire is around $40 million. Restoration required days of coordinated response and highlighted vulnerabilities in utility systems serving wildfire-prone areas. For this study, remote sensing data from several days prior to the Monument fire was analyzed and compared to current 2025 remote sensing data for the risk analysis. Objectives. The goals of my project were determining which electrical infrastructure is at higher risk for wildfire, determining how to define high-risk areas, creating a risk analysis to determine which areas are at higher risk than others, and conducting a cost analysis to mitigate wildfire risk to SSVEC infrastructure. The questions I wanted to answer were what types of poles and how many, whether they were wooden or metal, that are in high-risk areas, what type of overhead fuses are on power lines and how many are in high-risk areas, and what are the possible contributing factors to the wildfire zones, moisture index, temperature, precipitation, historical fires, or burned areas. The study area is located in the Sulphur Springs Valley of southeastern Arizona. It encompasses most of Cochise County, along with parts of Graham, Pima, and Santa Cruz counties. It is approximately 5,700 square miles and mostly rural. The numbers on the map represent each wildfire zone. Wildfire zones 16 and 29 are the largest wildfire zones and have their numbers inside of the wildfire zones, while all the other wildfire zones have their numbers outside and next to their wildfire zone. 2,545 wooden poles, 157 overhead expulsion fuses, and 1,538 meters were identified in total throughout the wildfire zones. The data I used for my project was the Arizona County boundaries, and that was obtained from ArcGIS Living Atlas of the World. Fuses, poles, wildfire zones, service territory, and service locations were all obtained by the SSVEC GIS department. And all of these data sets are vector data sets. Landsat 9 of May 2025 and Landsat 4 from May of 2011 were both obtained from the United States Geological Survey, and those are raster data sets used for the risk analysis. All vector data sets except service locations were used for the cost analysis and the risk analysis. Here we have my workflow flowchart. The cost analysis up top shows that I use the SSVEC data and Living Atlas data and added it to ArcGIS Pro. Then I refined the wildfire zones, and next I calculated the statistics for poles and fuses. Down at the bottom for the risk analysis, I used the Landsat 9 and 4 imagery from USGS. Then I prepared that imagery in RStudio and imported it into ArcGIS Pro. Then I conducted spatial analysis by bivariate analysis for the fuse and pole cost analysis, and vegetation health and moisture level raster analysis for the risk analysis. And finally, the maps were created using layouts in ArcGIS Pro to present the data. Cost analysis methodology. First, I calculated asset statistics per wildfire zone. I got the poles and fuses intersected with wildfire zones, and then I was able to get the number of fuses and poles per wildfire zone. Next, I calculated replacement cost of poles and fuses. I assigned cost to the poles and fuses. So poles that were less than or equal to 30 feet, they were given a cost of $2,200, and poles that were greater than or equal to 35 feet were given a cost of $2,600. Each fuse was given a cost of $319. The approximate replacement cost, 6.44 million for steel poles and 412,000 for current limiting fuses. These costs do not include labor costs due to fluctuating costs for each job. The cost analysis shows that the high cost wildfire zones are shown in the color purple, and those zones are 16, 29, 293, and 401. Wildfire zone 16 was approximately 595,000. Wildfire zone 29 was 3.55 million. 293 was 202,000, and 401 approximately 381,000. Of the remaining wildfire zones, 19 were considered moderate cost and 7 were considered low cost. Moving into the normalized difference vegetation index, also known as NDVI. It is a remote sensing index used to quantify vegetation greenness, understand vegetation density, and assess changes in plant health. NDVI is calculated using the near infrared band minus the red band divided by the near infrared band plus the red band. For Landsat 9, that is bands 4 and 5, and for Landsat 4, that is bands 4 and 3. It is measured on a scale from -1, which is considered dead vegetation or bare land, to 1, which is considered healthy vegetation. Negative values were correlated to high risk due to dead vegetation. Values less than 0.285 were correlated to moderate risk due to stressed vegetation, and values above 2.85 were correlated to low risk due to healthier vegetation. So here we can see the risk analysis for NDVI of 2011. The average low risk area per wildfire zone was 0.50%. The average moderate risk area per wildfire zone was 19.25%. And then the average high risk area per wildfire zone was 80.25%. High risk is shown in the color red, moderate risk in the color yellow, and low risk in green. The NDVI 2011 chart here shows that wildfire zones 143 and 373 were outliers in the high risk category. Wildfire zone 143 is in the Saguaro National Park and is mainly comprised of saguaro cactuses that retain water. And 373 is in a canyon at the foot of the Coronado National Forest that receives water runoff from the national forest. The risk analysis of NDVI for 2025 shows that the average low risk area per wildfire zone is 3.41%. The average moderate risk area per wildfire zone is 27.44%, and then the average high risk area per wildfire zone is 69.15%. And vegetation is healthier than 2011 based on the risk averages. And again, the color scheme is the same as the previous map. The NDVI 2025 chart shows that wildfire zones 143, 284, and 373 were all outliers in the high risk category. Again, as mentioned earlier, 143 is in the Saguaro National Park and 373 is in a canyon at the foot of the Coronado National Forest. Wildfire zone 284 is the lowest risk zone due to being in an agricultural area. And the high cost zones, 16 and 29, are more moderate risk than they are high risk, while 293 and 401 are more high risk than moderate risk. Moving into normalized difference water index, also known as NDWI. This is a remote sensing index used to monitor changes in water content of leaves. NDWI is calculated using the near infrared band and the shortwave infrared band. Landsat 9 uses band 5 and band 6, while Landsat 4 uses band 4 and band 5. It is also measured on a scale of -1 to 1, where -1 is bare land and 1 is body of water. NDWI was categorized with no moisture and low risk categories. Any values less than or equal to 0 was in the no moisture category, which equaled high risk, and any values above 0.001 was in the low moisture category, which equaled low risk. The risk analysis for NDWI of 2011 shows the average low moisture per wildfire zone is 10.25%, and the average no moisture per wildfire zone is 89.75%. No moisture is shown in the color red, and low moisture is shown in the color green. The NDWI 2011 chart shows that wildfire zone 284 is the biggest outlier, and that is due to being an agricultural area. The risk analysis of for NDWI of 2025 shows that an average low moisture area per wildfire zone of 13.11%, an average no moisture area per wildfire zone of 86.89%. The moisture levels are higher than compared to 2011 based on the moisture averages. And again, the color scheme is the same. The NDWI 2025 chart shows again that wildfire zone 284 is the biggest outlier due to being an agricultural area. And visually on the map, you can see some green areas in zones 16 and 29, but it does not translate to the graph because the areas are so big. So 16 and 29 are predominantly no moisture. Conclusions. NDVI averages are higher in 2025 than in 2011, indicating improved vegetation health. NDWI averages are slightly higher in 2025 than in 2011, indicating similar vegetation moisture. Cost analysis shows wildfire zones 16, 29, 293, and 401 are high cost zones. Additionally, 19 wildfire zones are considered moderate cost and 7 low cost zones. The pole replacement cost is approximately 6.44 million, and the overhead fuse replacement cost is approximately 412,000. Implications. So SSVEC should address wildfire mitigation based on the cost analysis due to healthier vegetation and higher moisture levels per wildfire zone in 2025 than pre-fire levels in 2011. Replace overhead expulsion fuses with current limiting fuses and wooden poles with steel poles. A phase-based replacement per wildfire zone starting with high cost areas then moving to moderate cost areas, and then finally low cost areas. And annually monitor NDVI and NDWI values to assess changes to risk analysis. And with that, my presentation is complete. Does anyone have any questions?